It uses AI to bring AI.
Race for artificial intelligence seems to have gone in overdrive. A few months ago, we told you about an app called CHATGPT. Since then, thousands of models has been released that use generative AI to create new content and make your experience more easier and more accurate. One of the areas of recent development in language models is to customize these models for specific use case. Considering that in mind, Google recently released a model for healthcare called MEDGEMMA 2. In this video, we will deep dive into the model. But before we do that, please like and subscribe for more content related to AI and robotics. Also, please comment if you have any other model that we should cover in our videos.
MEDGEMMA 2 harnesses the power of Google LLMs, aligned to the medical domain to more accurately and safely answer medical questions. It achieves this by leveraging a combination of base LLM improvements, medical domain fine-tuning, and prompting, and also use a novel ensemble refinement approach. MEDGEMMA 2 scored up to 86.5% on the MedQA dataset, a diverse benchmark for medical question answering, spanning medical exams, consumer health, and medical research. There were two main kinds of datasets that were used in the MEDGEMMA 2 paper. The first one was the multiple choice questions dataset. The second one was the long form medical questions. For the multiple choice question dataset, they used MedQA, MedMCQA, PubMedQA, and MMLU clinical topic dataset. For evaluation on long form questions, they basically collected datasets from MultiMedQA consisting of 1066 questions sampled from different sources. They also generated two new adversarial datasets for potential harm and biases. This includes a general adversarial dataset for health equity, drug use, alcohol, and mental health, and the health equity focused adversarial set that prioritizes use cases on health insurance, social, and environmental factors. Base LLM for MEDGEMMA 2 is none other than PaLM 2, a new iteration of Google's Pathway large language model with substantial performance improvement on multiple LLM benchmark tasks. They applied instructional fine-tuning to the PaLM 2 LLM. Instructional fine-tuning is the fine-tuning a language model on a collection of tasks described via instructions and instruction templates, thereby improving the zero-shot performance of large language models on unseen tasks. They trained a unified model which is optimized for performance across all datasets in MultiMedQA using dataset mixture ratios. They also use few-shot prompting by preparing example inputs and outputs before the final input, thereby improving performance further. Another strategy that they use was chain of thought augmentation, which involves augmenting each few-shot examples with a step-by-step explanation towards the final answer. The approach enables an LLM to condition on its own intermediate outputs in multi-step prompts. By crafting CO2 prompts to provide clear demonstration how to appropriately answer the given medical question, they improve model performance significantly. Self-consistency is a strategy introduced to improve performance of multiple choice benchmarks by sampling multiple explanations and answers from the model. The final answer is the one with majority of votes. Another approach they used was ensemble refinement, which is a two-stage process. First, given a chain of thought, prompt, and a question, the model produces multiple possible generations stochastically via temperature sampling. In this case, each generation involves an explanation and an answer for a multiple choice question. Then the model is conditioned on the original prompt, question, and the concatenated generation from the previous step, and is prompted to produce a refined explanation and answer. To assess the performance of MEDGEMMA 2, they ran a series of human evaluation tests. Human evaluation tests were performed by physicians and layperson raters. Physician raters were drawn from a pool of 15 individuals, 6 based in the US, 4 based in the UK, and 5 based in India. Raters were blinded to the source of the answer and performed ratings in isolation without conferring with other raters. In addition to the independent valuation of each response, a pairwise preference analysis was performed to directly rank preferences between two alternative answers to a given question. Raters were presented with a pair of answers from different sources. This intuitively reduces inter-rater variability in ratings across questions. On the statistical side, confidence intervals were computed via bootstrapping in 10,000 iterations. Two tail permutation tests were also used for hypothesis testing. Inter-rater agreement was measured as Randolph's kappa. This measurement was more appropriate than measures like Krippendorff's alpha, given the low baseline positive rate for several axes, such as incorrect comprehension. The measure assumes a uniform probability distribution for all raters and categories. An increasingly important concern given recent advances in large model pre-trained on web-scale data is the potential for overlap between evaluation benchmarks and training data. Google searched for overlapping text segments between multiple choice questions in MedQA and the corpus used to train the base LLM underlying MedPalm2, thereby reducing the overlap between the two. Here we covered all the important sections of the paper. The last part of it is the results section. Let's hear from Google how are the results of their model.
So the way we started with MedPalm2 was really to take PalM2, which is Google's most advanced language model, and then adapt it to the medical domain. To train the MedPalm2 model, we worked with a panel of clinicians across the US, the UK, and India. We took a representative set of answers from this panel of clinicians and then tuned the model to produce answers that look more like those answers. And from there, we used this panel of clinicians and their judgments to kind of evaluate whether these models were performing better across a set of human values, including things like low likelihood of medical harm, alignment with scientific consensus, precision, and a lack of bias. One limitation of existing work was that there was no standard way to evaluate a large language model tuned for the medical domain. So we introduced multi-MedQA, which is a benchmark for large language models in the medical domain, which spans consumer research questions, medical exam questions, and also consumer medical questions. To better encode a set of ethical principles into the MedPalm2 model, what we've done is a bunch of adversarial testing so that we can take the model, test it in scenarios that it might not have been kind of originally intended for, and make sure that its outputs are aligned with our values.
Capabilities that we need to further add to these models. One aspect that we are very excited about is multimodal, where a model is not only able to understand text, but also interpret your medical record, or understand and interpret your medical images such as your CT scans, or maybe even genomics data or protein sequence data. So I think the potential is immense, and as long as we do this safely and responsibly, but also boldly, I think we are going to have a lot of impact in the world. There is still a lot of research to be done, but I am very optimistic that we can get there.